Some moments in astronomy feel less like new discoveries and more like the opening of a door that was never supposed to stay closed this long. That is exactly what happened when the Vera Rubin telescope captured its first images. At first glance, they look like beautiful photographs of space. But the longer you stare, the stranger they become. Millions of galaxies packed into a single frame. Stellar nurseries glowing with violent beauty. Asteroids slipping through the darkness like quiet intruders. It suddenly becomes clear that this is not just another telescope taking prettier pictures. This is a machine built to watch the sky change over and over again until the universe stops looking like a frozen postcard and starts behaving like what it truly is. A restless, living system. The Rubin telescope was never meant to compete with observatories that stare deeply at one tiny target for hours or days. Its mission is much more radical than that. It was built to look wide, to sweep enormous portions of the sky again and again, and to catch whatever changes. That sounds simple until you understand the scale. This observatory sits high in the Chilean Andes, where the skies are dark, dry, and clear. And at its heart is one of the most extraordinary instruments ever built, the largest digital camera in the history of astronomy. More than 3 billion pixels. A machine capable of turning the night sky into a constant stream of high-precision data. And that changes the entire philosophy of astronomy. For centuries, telescopes have mostly given us snapshots. A still image of a galaxy. A still image of a nebula. A still image of a star field. Rubin is designed for something far more unsettling and exciting, repetition. It will scan the southern sky every few nights, revisiting the same regions again and again until motion, brightness changes, explosions, and hidden objects begin revealing themselves automatically. This is not just astronomy as photography. This is astronomy as surveillance of the cosmos. That is why the first images felt so overwhelming. They were not just proof that the telescope works. They were proof that the telescope sees on a scale that makes older expectations feel small. And the moment it opened its eyes, it immediately showed that the sky is much fuller, much more active, and much more alive than most people are used to imagining. One of the first released images centered on the Virgo cluster, and what it showed was staggering. At first, it looks like a dense sprinkling of light, but the truth is far more dramatic. Many of those specks are not stars at all. They are entire galaxies, each containing billions of suns spread across tens of millions of light-years. In one frame, Rubin captured a cosmic ocean of structure. Elegant spirals, giant ellipticals, warped systems, shredded collisions, and faint background galaxies glowing from unimaginable distances. What makes this image so powerful is not only the detail, but the combination of detail and scale. That is Rubin's true weapon. Other famous telescopes can show a tiny piece of the universe with incredible sharpness. Rubin steps back and shows the whole environment without losing the richness. It lets you see not just one galaxy, but the architecture of a whole region of the universe at once. It shows how galaxies relate to one another, how gravity stretches them, how collisions tear them into arcs and streams, and how clusters build their own complex history over cosmic time. That is why astronomers reacted so strongly, because this image is not just beautiful, it is useful in a profound way. Hidden inside that sea of galaxies are clues about dark matter, galactic evolution, and the growth of structure across the universe. The picture looks like art, but to science, it is also a map of invisible forces. Rubin's first look did not just give us a better image of Virgo. It gave us a glimpse of how the telescope will redraw the large-scale story of the universe. The second major image was completely different in mood, but no less astonishing. Rubin turned toward the Trifid and Lagoon nebulae, two immense regions of gas and dust inside our own Milky Way, and revealed them with a depth and breadth that made them feel almost unreal. These are not quiet clouds. They are stellar nurseries, places where new stars are being born right now. Rubin's image showed glowing hydrogen gas, blue reflection nebulae, and dark rivers of dust cutting through the light like scars. This image matters because it shows something Rubin does exceptionally well: context. It does not isolate one beautiful pillar of gas and turn it into a portrait. It captures the neighborhood, the entire tangled ecosystem of star formation. You can see how young stars are already reshaping the clouds that created them, carving cavities, blowing radiation outward, and turning quiet matter into violent structure. The result is not just a picture of beauty. It is a picture of creation under pressure. And once again, Rubin changes the emotional scale of what we are seeing. These nebulae are not just pretty objects hanging in space. They are active chapters in an ongoing process. With repeated observations over years, regions like these will no longer look static. They will become part of a longer record of how stellar environments evolve. Rubin is not only showing us where stars are born, it is preparing to help us watch how those birthplaces change over time. While the galaxies and nebulae captured the imagination, one of Rubin's most important early achievements was much quieter: asteroid detection. During its early observations, the observatory picked up moving points of light, slipping across the frame, small bodies drifting through our own solar system against the fixed background of stars. In just a short span of test observing, Rubin identified thousands of asteroids, including previously unknown objects. Some of them were near-Earth objects, and that fact immediately proved something critical. Rubin's alert system works. This is where the telescope starts to feel almost dangerous in its power, because Rubin is not just a deep space observatory. It is also a machine for catching motion in real time. It compares repeated images, notices what moved, what brightened, what faded, and what appeared where nothing had been before. That means it can serve cosmology, galactic astronomy, and planetary defense at the same time. It can map distant galaxies billions of light years away, while also tracking rocks much closer to home that might one day matter to Earth in a very direct way.